3.2a, implicit differentiation today is the topic. And it's day one. We'll take 2 days over this particular topic of implicit differentiation. So you're like, well, what the heck does implicit mean? Well, implicit is kind of the opposite of explicit. And explicit means that it's very shown, revealed, very obvious. And we think of functions like y equals x squared plus 1 as being an explicit function because it explicitly states the relationship between y and x. Okay. So what's an implicit look like? Well, an implicit is where we have different y's, different x's all intermixed, and it would be difficult to turn it into an explicit statement like y equals. So yeah, here we've got like y equals another explicit one compared with x, y to the third. It would be difficult to solve those. So if I can't necessarily solve those for y, how do I take the derivative? We're used to going dy dx equals. Well, we can still do that. We just have to pay attention to what the variables are, and when they're not x, we have to do a little bit of extra work. So let's just look at example 1, differentiating with respect to x. And so I'm differentiating x cubed. And if I'm differentiating with respect to x, this is easy. I get 3x squared. Just use the power rule. When the variables agree, it's very straightforward. When the variables disagree, we have an extra step. So I'm going to take the derivative of y to the third. It's just power rule. We know how to apply power rule. So this is simply power rule. But because y is different than x, I need to add in multiplied by the rate of change of dy compared to dx. So I get a chain off of dy dx. And this is the implicit differentiation rule that we pick up. So over here, I could have said I had the rate of change of x compared to itself, dx, but then that would just reduce down to 1, so that is the reason why we don't typically write dx dx. Now, with c, I can think of these as individual little rules, right? Plus the derivative, because it's adding and subtracting, so we can use our add-subtract rule of differentiation. And the derivative of x with respect to x would be simply 1. And the derivative, this is a y, doesn't look like a y. The derivative of 3y would be use power rule. It would give us just 3y to the 0 times dy dx. And that is what that one looks like. D gets to be a little bit more fun because D has the product rule. So I first examined and noticed, oh, I've got two things multiplying. So that says product rule. The next thing that hit me was the fact that I've got mixed variables. Product rule with mixed variables. And that's going to lead me into taking the derivative implicitly. So let's go into, we know it's f prime g plus g prime f, right? So derivative of x would be 1 multiplied by y squared plus derivative of the second function uses power rule, 2y to the first, implicit differentiation dy dx, and then times f of x, which is simply multiplying by x. So my whole g prime turned out to be 2y to the first. That first can sometimes be interpreted as a prime sign. It's not real clear there. So I'm going to take it out. Just go 2y dy dx times x. I may like to just format this to make it a little bit more readable. And I'd have y squared plus 2xy, alphabetically arrange those two variables, dy dx. And that is a multiplication of those, of all the terms, all the variables in the second term. All right, example 2. Find dy dx for y cubed plus y squared minus y minus x squared equals negative 4x. Well, we can see by the vertical line test that this is not a function. It is a relation. But yet it's kind of a cool curve. And they want us to find dy dx. Okay, well, let's do it. Implicit differentiation. Power rule is going to give us 3y squared. Since the variable is not x, it's going to be a dy dx. Plus 2y dy dx minus 5 dy dx minus 2x dx dx, but why write it, equals 0. Okay? I just simply use power rule along the way on all those y's. Now, you know what? There should have been the rules. I might have skipped that page. Yeah, I don't see it. Okay, on the bottom of yours, you have steps to doing these. And the first step says differentiate both sides of the equation with respect to x. We did that. Second step says collect all the terms involving dy dx on the left side and then move all the other terms to the right side. Well, when I'm examining our function here, or our first step, I have dy dx, dy dx, and dyx. I have 3 terms with dy dx, and then I have this little guy that does not. So I'm going to use that step 2 to move the 2x over to the other side. And then step 3 says factor out a dy dx, and then we'll solve for dy dx. All right. So it's just really algebraic steps from here on out. I'm going to have 3y squared plus 2y, and I'm not forgetting my dy dx. I'm just going to factor out dy dx from those 3, and then I'm going to move the 2x to the other side through addition, right? Add 2x, add 2x. This was my GCF, the dy dx. Anything not clear? Good. All right, so I have dy dx. I guess how would I know, right? You're probably like, how would you know if I don't get it? Well, what I'm hoping is if you don't get it, that you pause the video, rewind for 30 seconds, and listen to it one more time, okay? Or highlight it, put a post-it by it, and ask me questions when we are in class together, or if you want to Zoom with me, just ask that. I know it's not the easiest learning from distance learning. All right, so I solved for dy dx, which is like solving for a variable. And that caused me to divide by this entire factor on the left. Part B says write the equation of the tangent line at the point 2, 0. So now I need to evaluate my derivative to get the slope so I can write the equation of the tangent line. All right, so let's take dy dx and evaluate it at the location 2, 0. Oh, this is different. Usually we evaluate just at an x value. But notice our derivative now contains x and y's, so I need both the x and the y value of the coordinate pair. So I'm going to end up with 2 times 2 over 3 times 0 squared plus 2 times 0 minus 5. Show you all the detail on that line. Let's evaluate it. We'd have 4 over negative 5, which would be negative 4/5. We have our slope. Now let's write the equation of the tangent line. The equation of the tangent line. Right here. Equation of tangent. You know what? Go draw it in first. Let's go up here to 2, 0, and let's sketch in our tangent line. It would look something like that, correct? I hope that we had a negative slope. Did we? Hey, we did. Beautiful, because that aligns with our thinking. Now, y minus y1, the y1 value is 0, equals the slope, negative 4/5. By now, we've written so many equations of tangent lines that I'm hoping you aren't wondering where is she coming up with this stuff. If you are, highlight it, post it, and ask me. Now, Hang on 1 second. All right, we've got the equation of the tangent line. I realize it could be simplified. If you feel like doing it, go ahead. Part C says find the slope. Find the slope of the normal line. And you're like, what the heck is a normal line? Never had to do that one before. You're right. The equation of the normal line is new. And you have a little box down here. Let me move myself. You have a little box that says the normal line is defined as the line that is blank to the tangent line at the point of tangency. It's a lot of words there. Reread it. The normal line is defined as the line that is perpendicular to the tangent line at the point of tangency. All right. So we know the normal line is perpendicular to the tangent line. Let's go draw it in. Here's that point of tangency, 2, 0, right? That's where we drew our tangent line. Now, let's draw in the normal line. I'm going to just kind of dash mine in. It runs perpendicular, and it should meet up in perpendicular style. Right underneath this, it's the normal line. Because yes, a normal line can be tested on the AP exam. Just about everything we do can be tested on the AP. There are so many things in Calc AB. We got a lot of topics, a lot of new topics for you. So tangent line, normal line. Now, how would I create the equation of the normal line? Well, I need a point, don't I? And my point remains the same. It's 0, 2. Oops, I'm sorry, it's 2, 0. It's 2, 0. What is the slope? Well, I'm just going to make for the record here. Tangent slope was calculated to be -4/5. Now, without me even telling you, I would expect you to be able to create a perpendicular slope. Have you done that in previous classes? Absolutely. So, drawing on previous knowledge, we want to get the normal. I'm going to write normal line slope rather than just saying normal slope because that's kind of vague. The normal line slope runs perpendicular to it, so it is opposite reciprocal. Pen's not writing very well. Reciprocal to tangent slope, right? Write as much as you need to remember that. So what's my slope? Well, my slope's going to be opposite, so I'm going to have a positive, and it's the reciprocal, so 5/4. Now can I write the equation of the tangent line? Or the normal line? Absolutely. Y minus 0 equals 5/4 x minus 2. And there you got it. If you want to make it look nicer, take out the minus 0, right? And there we have it. So not hard. And what else we got to do on this one? We got a couple more examples to go through. Let me clear my screen. Going on. Find dy dx. And, ooh, I took a look at that equation, and I didn't really like what I saw. Because here I see product rule, and here I see product rule. We got to do 2 product rules. All right, that's not so bad. F prime g plus g prime f. So 2xy plus y, the derivative of y would be 1 dy dx times x squared. Added with derivative of the other one, that was the first product rule, into the second product rule. 2y, that's power rule. Got to take account that the variable is not x, so dy dx, and then multiplied by the first. Plus derivative of the second thing, which is 1, multiplied by the first function, y squared, equals 0. Now, let's do some enhancements here. First power rule, is there. Second power rule is here. If you want to identify, you would have had f prime g, and this would have been g prime f. Here we had f prime g times g prime, I wasn't going to underline that, f, right? If you wanted to know where all those parts came from. Well, this looks pretty crazy. I'm going to kind of come back to the steps that are in that box at the lower side of the first page. It says collect all the terms involving dy dx onto one side of the equation, all the others to the other side. I'm going to keep the dy dx's on the left side because that's where they are right now. So let's go and keep these things the same. I have an x squared dy dx. Just be sure that you account for each and every term so we don't miss one. Ooh, that x there I just noticed. I probably want to put that in front. So 2xy just to make it pretty. Then those are the only two things with dy dx. So the other items are going to flip to the other side of the equal sign, and I would do that through subtraction. So I'm going to minus 2xy, and I'm going to minus the y squared. Follow? Now let's factor out. So this is kind of sorting. Basic algebra. Next, let's GCF the dy dx. So I'm going to have x squared plus 2xy times dy dx equals, the other side doesn't really matter, negative, I'm going to pull the negative, negative 2xy plus y squared, just to keep you guys guessing. All right. Next, I'm going to have solve for dy dx. So dy dx equals, I got that negative sign out front, 2xy plus y squared over dividing by that factor from the left side of our equation. And there's the, oops, get a parenthesis. Don't want to leave mismatch parentheses. Delta Math and WebAssign would not like that. There's our derivative. And I think we have one to go. The last one. Oh, of course, we got to get some e's and signs in here. So sine of 3y, that's going to have some implicit to it because of the mixed variables. Oh, the e to the y will have some implicit as well. So chain rule stuff. What I don't see is any product rule or quotient rule, so that's good. So I'm going to have 2. The derivative of e to the y is e to the y. Chain off, take the derivative of y, which will give us 1 dy dx. Then this will equal 2x dx dx, but I don't really need to write it, plus derivative of all the outer function gives me a cosine, leave the inside alone, times the derivative of the inside, which gives me 3 times 1 dy dx. I'm not going to put the 1 down. Okay. Now, do you want to make some notes to yourself? This was derivative of e to the y. This all was derivative of sine. F prime g of x times g prime of x, the chain rule. This was chain rule. Both of them had chain rule. All right, now it is the sorting game. I want dy dx's on one side, and I want everything else, all the other terms, to the other side. So I need to bring this entire thing over to the left side, don't I? Or at least that's where I'm going to collect my dy dx's. So This is going to come over through subtraction. I'm going to have 2 e to the y dy dx. I'm not going to do too many steps here at once. Minus 3 cosine 3y dy dx equals 2x. You can see what changed from line 1 to line 2. You can see what I did. I subtracted that whole group. Now, let's GCF. So we sorted. We're going to GCF next. So I'm going to have 2 e to the y minus 3 cosine 3y, all of that, so big brackets, times dy dx equals 2x. Finally, solve for dy dx. And dy dx, I just need to divide by that entire multiplier, which is why I put it in, well, it needed some sort of brackets, but it all moves to the other side through division. E to the y minus 3 cosine of 3y. And I like it. It's all done. I hope I did the steps slow enough and with enough steps that you can follow. You have a worksheet that'll take you through some more implicit differentiation. Looks like these beginning ones, I see a little product rule right there. Maybe jot that down so you don't mess that up. Little chain rule. Five and 6 do not look too bad. You know, chain rule, chain rule. Ooh, lots of chain rule. Yeah. All right. Good luck, you guys. Thanks for being patient.